For this part, we're going to do some design problem. So please read the questions on the screen and think about what kind of algorithm you might use and their runtime and space complexity. So I hope you did that. And so the most intuitive solution would be using sorting algorithms, right? So what you can do is you can just count the frequency of each word and sort the words with a custom order relation that uses these frequencies. Then take the sublist of k items. So it means that we're going to use collections that sort and implement our own comparative method. So we know that we can use the collections that sort because list is essentially part of collections of Java, right? Yeah. So that's one word source algorithm, but what are the time complexity and space complexity, right? So, oops, yeah, so the complexity here. So the time complexity is would be n log of n, where n is the length of the words. We count the frequency of each word in O of n times. Then we sort the given words in n log of n time. Because we are not really eliminating any items, right? We are gonna sort the n I. We are gonna insert n items and sort n items, and then I build yeah. So the sorting would take log of n. So space complexity is saying O of n because we have to use a space to store our this candidate's words. So, but then let's say we have a constraint that we must use heap. Why? Because we're learning heap. So what are the invariants of heap? So first, the height of heap is log of n, and then also, but we have another interesting invariant which is binary tree invariance, right? So which means that for heap, each element has a key that is less than the keys of its children. But then unlike binary search tree, the left doesn't mean it's less than its root of its parents, right? So left and right does it's we in a mean heap we know that it's the root is definitely smaller than his children, but then the left and right are not necessarily related in any way. So first, we know that some common operations in heap will be percolate down and percolate up to maintain this invariance that we mentioned above, and then we know that this will run of log of n due to the height of heap, right? So let's come up with some solution. Hopefully you had some time to think about it. So let's think about some constraints first. So it says, how does the idea of type k relate to the heap? What does that mean? So let's say we're looking for top three words. Then your heap should have some kind of three words, right? So let's say I love cookie. Then this I love cookie are three most frequently used words and it'll be inside of your heap. So you can think about, oh yeah, it's something to do with a size, right? But with that in mind, I'm just going to quickly go over this runtime and time complexity as we know that we are going to use heap. So first, we need to at least iterate the list still once. So there'll be O of n, where n as number of elements. But here, the difference is whenever we insert the item into heap, it might percolate down or up. That's still gonna be log time, right? But then we're actually only gonna do that k times. So it'd be log of k, unlike log of n, where compared to where we are using this Java collections of sort, right? So space complexity, like you probably guessed, if we still O of n, because there's still n is the number of items, right? So let's demonstrate, but before even heap, you probably thought about how we are going to keep track of those frequency and a key value, right? So it's key value pair. We can definitely use a map in our map ADT, right? So button for map, um, it has hash set and tree hash map and tree map, but then we don't really care about ordering of those words, so we can just use hash map, which tends to have a faster runtime. So like this are just arbitrary like order. So I appear twice, liquid appear once, love appear twice, coding appear once. So these are the results of this map. There'll be a hash map. Then we're going to think about how we're how we want to sort in our priority queue, right? So it's not just like regular sorting. We have to make our own comparative method. So here's a one really common way, right? First, we want to compare it by our frequency, which would be the frequency of the words. But if the frequency of those words are the same, like that is specified in the question, we want to order them by like geographic order. So then we will compare, then we will do that comparative method, right? Yeah. So, but then you seem like, oh yeah, this is too long for some fancy people. Uh, oops. And this is how you can give it is compare method, right? Here, you have mean heap. So you can use actually lambda function. So what lambda function does, it's the same thing as the previous slide, just compare method. But here, we just simply use this like arrow thing, which is it's also called arrow function in different language, but here lambda, you're doing the same thing. We're using ternary operator to make it concise code, but it says if your frequency are not the same, then we want to just sort them by frequency. Else we want to compare them, compare like alpha, because we want to return alphabetically, right? If those frequency are not the same. Yeah, so don't get too stuck up on those small like syntax, but just know the general idea. That's why we're here, right? So, but then the idea is okay, so we have counted all the frequencies and all the words, all good, that, and but the question is, how are we going to, what kind of idea are we gonna use to maintain size k? The most intuitive solution would be using mean heap. If you think about it, whenever you're offering the items, your heap is going to maintain the invariance, right? So if you use mean heap, it means the smallest frequency are always going to be the top. So whenever we exceed the size of k, which is more like top worse than what we are looking for, then we can just pop it. We can just pull it, right? So here is more visual examples. So let's just assume that the coding is here. We inserted coding first and then love. So this is frequency 1, frequency 2, great. And then now we inserted lead code. So 2, 1, 1 in frequency, right? So that's good, but then here we have a problem. It says now the size 3 is actually greater than our k, right? Which means that we have more top words, keywords what we need. So we can simply pop coding, then this is what we are going to have. And the last word, we are going to insert I. So now we are maintaining the invariants, but then here we do have a size 3 that is greater than our k, which is 2. So then we can simply public code, because we know that in this example, in this stage, lead code has the smallest frequency. Therefore, what's going to be left is love and I. And then I believe the question asks you to return it as a list, so you can just simply pull this leftover, whatever it is left in the priority queue, and then add it to your list, and then return that. So here I just really wanted to think about what first come with some brute force solution for your own sake, and then think about time complexity and space complexity, and then think about from here where can I improve. But we were given heap, so what kind of heap invariants do we have, and how that can be beneficial in solving this problem, right? So I hope this helped.